All right, here are solutions to problem for quiz 1 for Math 252. What we have here in this first problem is we're evaluating some limits, but told to do so without using L'Hopital's rule. L'Hopital's rule would apply here. If you plug 3 into the numerator and the denominator, you get 0 over 0. So it is an indeterminate form, but since it says not to use L'Hopital's rule, we better not use it. So what are we going to do instead? Well, what you can do here is some factoring. So the numerator would factor as what, x minus 3 times x minus 1? And the denominator would factor as x minus 3 times x minus 3. And I'm not surprised to see an x minus 3 in common in the numerator and the denominator. That's what caused this to be 0 over 0 in the first place. But at any rate, this expression is equal to this expression. And in this expression, I can cancel out these x minus 3's. You got to be a little bit careful there. You can't just cancel them in any expression, but because I'm taking limits here, I'm not concerned with the value when x equals 3. So I don't have to worry about dividing by 0. I can cancel out those x minus 3's and say that this is equal to the limit as x approaches 3 from the negative side of x minus 1 over x minus 3. And then we can evaluate this limit here. Let's see, if x is approaching 3 from the negative side, I'm thinking like 2.999, I guess. What I get here is some number really, really close to 2. And what I get down here is some number that is really close to 0, but slightly negative, because I have a little less than 3 and I'm getting rid of an entire 3. So I'm slightly negative. So I have this number close to 2 divided by a number that is close to 0 but negative. That limit is equal to negative infinity. And maybe I'll even write this is 2 over 0 from the negative side, if that helps you think about that. So this would end up being the answer. And we can move on to the second problem. Here you have to evaluate the limit as x approaches negative infinity of this expression. And there's a couple ways you can do that. One way you can do it is with logs. You don't have to use logs. But one way you could do it is say, well, if this is y, then the natural log of y would be equal to the natural log of this whole thing. And the natural log of a limit is the same as the limit of that log. This is one of your log rules. So I can say this is the natural log of 2 raised up to this ridiculous exponent x cubed plus a bunch of 9s and an x squared. I think I got that right. And the advantage of having natural logs in there is you can apply your third log rule, which allows you to take this exponent and move it down in front. Say that the natural log of y is equal to the limit as x approaches negative infinity of, I'd have x cubed plus all these 9s, which I'm already sick of writing, sorry, times the natural log of 2. So to evaluate this limit, either you can say, well, kind of the largest exponent wins, so I can ignore all of this stuff and think about what would happen to x cubed as x approaches negative infinity. Or if you want to write it out in more steps, you can factor out an x cubed. So now I have kind of an overabundance of parentheses, x cubed, and then 1 plus all these 9s divided by x, because I had an x squared on the bottom, but kind of divide by x cubed leaves me with an x down on the bottom, times the natural log of 2. So note that if I'm evaluating this limit as x goes towards negative infinity, any number, even though if it looks big here, when I'm dividing it by something that's approaching negative infinity, this all turns into a 0. So I get 1 plus 0. In other words, what's inside the parentheses is just 1. So what that tells me is that the natural log of y is just equal to the limit as x approaches negative infinity of x cubed times the natural log of 2, which is just negative infinity. Negative infinity to the third power if you want. It's still going to be negative. And it tends towards infinity, and multiply it by a positive constant. That makes no difference. What I'm saying is the natural log of y is equal to negative infinity, which is not the answer to the question, because y is the answer to the question. Y is what I set this thing equal to. But I could solve for y. I could say y is e to the negative infinity, which is the same as 1 over e to the infinity if you want, which is just 0. So the answer ends up being 0. You don't have to do it with these logs, but if you wrote it with logs, great, good for you. Number 2, use L'Hopital's rule. So if you're going to use L'Hopital's rule, you better make sure you have an indeterminate form. If you plug 0 into the numerator and the denominator, you'll get 0 over 0, because the sign of 0 is 0 and 0 minus 0 is 0. So what that tells me is that I can use L'Hopital's rule and say that this limit is the same as the limit as x approaches 0 from the positive side of the derivative of the numerator, which would be cosine of x minus 1, and the derivative of the denominator would be 4x cubed. And note that this is still an indeterminate form. Maybe I'll even write this is 0 over 0, so I can use L'Hopital's rule again. The derivative of cosine is negative sine. Let me write my limits first. So I get negative sine x plus 0 if you want, divided by 12x squared. And it continues, because if you go plugging in zeros here, you'll again get 0 over 0. So I can use L'Hopital's rule again. The derivative of negative, write my limits first, of negative sine of x is negative cosine of x divided by 24x. And you're like, oh, I see where this is going. Eventually the variables are going to disappear in the denominator. No. Well, that is true. You can't take the derivative again because this is no longer an indeterminate form. Maybe I'll say, note, this is not an indeterminate form. That's important. That means you can't use L'Hopital's rule again. You've got to evaluate the limit right here. The limit as x approaches 0 from the positive side of this thing. Well, let's see. Cosine of 0 is 1, so the negative of that would be negative 1. But down on the bottom, I'm approaching 0 from the positive side, so I'm kind of thinking about this like negative 1 over positive 0, which is negative infinity. I'll write that for your reference. All right, what about B here? This is an indeterminate form, but you can't use L'Hopital's rule immediately because it's not written as a quotient. So what I can do is I can rewrite it as a quotient. Maybe I will write it as x to the negative 1 power instead of multiplying by x, divide by x to the negative 1. And then note that if you plug 0, a number slightly greater than 0 in here, you get negative infinity. And you plug in a number slightly greater than 0 here, you get positive infinity. That's one of those infinity over infinity indeterminate forms. So we can use L'Hopital's rule. The derivative of natural log of x is 1 over x. I keep forgetting to write my limits before I start talking. The limit as x approaches 0 from the positive side of 1 over x, this derivative. This derivative is negative, the negative of x to the negative 2 power. X to the negative 2 power is 1 over x squared. Maybe I'll write it like that. So this, using algebra here, not L'Hopital's rule, is negative x. Right? I could flip this fraction upside down and I'd have x squared over x, which is just x. The limit as x approaches 0 from the positive side of negative x is just 0. So that ends up being the answer to this guy. And I guess what I'm doing is I'm putting boxes around my answer, so I'll throw one up here. Move on to the second page, antiderivatives. We're told the derivative of some function is this guy, and we're asked to find the antiderivative. So it'll be kind of 2 iterations, first to get to the function, and then to find the antiderivative. So let's first find f of x. Actually, what I would first do is rewrite this thing as 1/2 x to the negative 2 power plus x squared. Makes it a little bit easier to find the antiderivative. You leave the constant alone, and then with the x to the negative 2, if you added 1 to that exponent, you get negative 1. So if I put a negative 1 here and then a negative 1 here, then if I were to take the derivative, this negative 1 and this negative 1 will cancel, and this will turn into a negative 2. Looks like I got that right. And then this antiderivative is add 1 to the exponent. We need a 1/3 as the coefficient here to make sure that I don't end up with a coefficient up there. And then tack on a constant. So here's kind of a general form of your function, but you're told that f of 1 is 11/6. So what that tells me is that 11/6 must be equal to negative 1/2, which is this guy, plus 1/3, this guy, plus c. But negative 1/2 plus 1/3 is negative 1/6. This is negative 3/6. This is positive 2/6. And if I add 1/6 to both sides, I get that c is 12/6, aka 2. And that's great and all, but that's not the answer. That's just your function. You want to know the antiderivative. So to figure out the antiderivative, I can say, well, let's kind of think about, let's see, do I have to write this somewhere? Okay, let's write this somewhere. My function is negative 1/2 x to the negative 1 power plus 1/3 x to the 3rd power plus 2, which is what I solved for c to be. So if I want to find the antiderivative, I'll leave this constant alone. And then for the x to the negative 1, I'll remember that the antiderivative of 1 over x is the natural log of the absolute value of x. And then the antiderivative of 1/3 x to the third power, well, it'll be x to the fourth power, but I'll need to bring a 1/4 down in front. So in total, my coefficient is 1/12. I get 1/12 x to the fourth. The antiderivative of 2 would be 2x. And then tack on another constant. Maybe I'll use the letter d now since I use c over here. And if I could solve for d, I would be done, and I can because I know that f of 1 is 13/12. So 13/12 is equal to negative 1/2 times the natural log of 1, but the natural log of 1 is just 0, plus 1/12 times 1, plus 2 times 1, plus d. Wait a minute, this is just 0 right here, and if I subtract 1/12 from both sides of the equation, I get 12/12, aka 1, is equal to 2 plus d. So therefore, d is equal to negative 1. And my antiderivative, f of x, would be, let's just copy this thing, negative 1/2 natural log absolute x plus 1/12 x to the fourth power, or x to the fourth over 12 if you prefer, plus 2x minus 1 for d. And finally, that takes me to the last problem here. Problem, I don't know, you're like, oh, decimals, what a jerk. Yeah, I'm not gonna lie, I made this a little trickier than I probably had to. Estimate the area under this curve from here to here by calculating M4. Well, to calculate M4, you're thinking I'm adding up the area of 4 different rectangles, and to figure out the length of each of those rectangles, I can think about the entire length, so 7.5 minus negative 4.5, which ends up being 12. But that's the total length. I want 4 rectangles in that length, so each individual rectangle, 12 over 4, which is 3, is my rectangle length. Which is already kind of annoying because I'm using midpoints. So what that means is I will want the point that is 1.5, half of this from the left endpoint and 1.5 from the right. But okay, so let's deal with it. Maybe I'll just start calculating. So M4 is equal to a sum of 4 things. Each of these rectangles have a length of 3. So 3 times something plus 3, well, maybe I won't write it all out. But how do I figure out that something right there? I think it might help to have a number line. So here is negative 4, negative 3, negative 2, negative 1, 0. 1, 2, 3, 4, 5, poorly planned. 6, 7, 8, fine. So I'm talking about, maybe in a different color, negative 4.5 all the way up to 7.5. And each of my rectangles has length 3. So my first rectangle goes from negative 4.5 to negative 1.5. And my next rectangle goes from negative 1.5 up to positive 1.5. And my next rectangle goes from 1.5 up to positive 4.5. And my last rectangle goes from 4.5 to 7.5. And you're like, oh my god, all these 0.5s, how annoying. Well, if you look for the point that's halfway between these two guys, the halfway between, you could add them up and divide by 2, or you could say they're 3 apart. So halfway there would be 1.5 more. 1.5 more, this midpoint right here would be 3. And this midpoint right here would be 0. And this midpoint right here would be 3. And this midpoint right here, halfway between 4.5 and 7.5, would be 6. So these will be the x coordinates that I use to figure out the height of the each of the rectangles. This is negative 3 here. So my first rectangle, it has length 3, they all do, but it has height of whatever the height of my curve is at negative 3. So I'm going to take negative 3 and put it in here. I got negative 3 squared minus negative 3. And then to that I am going to add my next rectangle, which will be 3, is again the length, times And now I'm going to use 0. So 0 squared minus 0. And then my next rectangle, maybe down here, is again going to have length of 3. And now I'm going to use 3 in the function to estimate the height. So I get 3 squared minus 3. And then my last rectangle, I'm going to use 6. So the length is still 3. But to figure out the height, I'll put 6 into this function, or this curve, and get this height. So when the dust settles, let's see, I got 3 times, this is 9 minus negative 3, that's 12. Plus 3 times, this is 0. Plus 3 times, this is 9 minus 3 is 6. Plus 3 times 36 minus 6 is 30. You might be able to add up all those numbers, or if you're lazy like me, you might factor out a 3 and get 12 plus 6 plus 30 left over on the inside here. So I get 3 times, what's that, 48? Well, 3 times 50 is 150, so 3 times 48 would be 3 2s less than 150. It would be 6 less than 150, aka 144. So that'd be the answer to this question. Sorry, that was kind of annoying. I did that on purpose, using these using these decimals and negative numbers and all, because I figured it would really help you. It's a really beneficial skill to have a strong intuitive understanding of how to find these midpoints and all these different boundaries. But that was definitely a challenging question. End the video here.